We can go.
Okay, so finally, today, we are gonna see an autoencoder, how you really do it, in practice. So first of all, credits to the guy that did the Jupyter notebook. I hope he wrote a lot of, we went through many times and he wrote a lot of comments, and so this should be self-explainable. I understood that, so probably you will do that much better than me. So ingredients that we are using today is the Jupyter notebook. You probably are familiar with. You can mix code and the text in the same notebook. Colab is online cloud service from Google that allows you to run GPUs, TPUs, and other software, and then you can run this Jupyter notebook. In the past, you had to download specific software. Now you can do it, online. It should be easy. Also, you just connect. You just go to the link and you execute, and then you can copy the notebook. I think I made it only readable, just to not mess it up and not really to avoid that you touch it. Actually, you are encouraged to get it, copy, and modify as you prefer. Python is the language that is used, widely used in AI and machine learning, since there are many libraries, and in particular, we are going to use Keras. TensorFlow is another one, Keras, we are going to use today. And we will implement what we were discussing in these days. So I think that, the important part is that, again, since I want to give you let's say, a sense of how a physicist can use AI, I want to start from, what the problem is. We discussed it extensively the first day. Just to remind you, we are trying to establish or to have a full streaming without DA2. That means that you are expecting that each subdetector, each channel of each subdetector goes straight from the beginning to the end without going under supervision of a trigger that says this is interest, this is not. Okay, this was the basic point that we started 2 days ago. This means that you have a long way to go from here to writing down or elaborate your final information. And there is at the very beginning where all streams are, going through, that you have to have a powerful network that allows this communication. And one way, if the rate is not reducible, you cannot reduce the rate, because we made an example that you reach, for instance, for EPICS, you listening these couple of days detectors from EPIC detector. And Dual Reach has the silicon PM that produces a signal at the level of 1 photoelectron at 1 megahertz per channel, and you cannot do much if you don't see multiple pixels, one close to another, to identify a ring that corresponds to a particle. The only way is just to bring this information along the way, string it along the way, and at some point have a correlation, a spatial correlation of your hits in order to be sure that you have something that is close to a circle. This is because the light produced by Cherenkov emission is so tiny, so small, that you are easily confusing the single photon produced by this light with the thermal emission of the silicon PM. So in this way, in this case, it's impossible to reduce. If you are, obviously, if you have any time information, if I know that I'm just sampling, I'm just taking data when my particle is crossing, this can help. But we said that the streaming doesn't want to use a trigger. It would like to just stream all data out, and at some point do this kind of, combination of the information. So the only way, again, if you think about the traffic on the network, the only way to reduce the traffic, the data volume that you are moving from one point to another, either you reduce the rate or you reduce the size. And this is why the compression of data can be, a possible tool to reduce the load on the network. So this is, in particular important for streaming without. So the use case we discussed is actually one important ingredient to use dual reach in streaming mode in edX. So it's not just academic, it's a real problem that we are trying to face, we are trying to solve in this way. So point is that we want to compress the waveform, and we also discussed why it's important to get the waveform, in particular for this pile up. At some point, I want to be sure that my signal is only a one peak and not two peak overlapping, because if not, if you just calculate the charge, it is a very efficient way to transform the information embedded in these 48 samples just in a single number, maybe a couple of numbers, one to get the energy, and in the other case, for instance, the position of the peak or a threshold to get the timing associated to that specific peak. But we said that we want at least to have the capability at some point to decompress the data and be sure that what we assume to have a single peak, so the charge associated to a signal, was really the area of a single peak waveform, and not the overlapping two that can easily give you, twice the charge, and then I can get confused and interpret that as a twice the energy deposited by that specific interaction. So this is the reason why we want to keep possibly the entire waveform, but on the other hand, we are trying a way to compress this information. Again, here is we'll see running the Jupyter notebook that the information is not only, related to the peak. There is another things that I didn't mention, that when you sample with a digitizer, a flash ADCs, one of the problems you have that any continuous baseline that you may have below your signal, and then you integrate, this is, you're calculating the area of a curve, so you have to be sure that it starts from zero. Okay, this is called baseline, so it means that before to calculate the integral, you want to be sure that it starts, from the right point. So you have to calculate, you have to guess out of the waveform itself where the baseline is. Baseline is usually due to a current, a continuous current entering in some way, pick up by the detector, pick up by the electronics, whatever it is. You may have, this level that fake your data if you just calculated the integral. So the usual way is you subtract this line here. So what you do is take a part of out of the peak region and say my baseline is corresponding to a certain value. So I take my sample. Okay, here is time. I hope if anything is not clear, please interrupt me and ask. This is time. This is voltage. Okay. And again, here are, this seems to be continuous, but actually is digitized. It is a 48 sample. And the value that you have here, as you can see, is not zero. So step zero, you want to, identify the region outside the peak and subtract that. This is the baseline. And this is, the prepared signal that then can be interpreted, can be fed to the AI machine learning algorithm. At the end of the day, we are anyway interested to the charge, to the integral of this peak, only the peak, and then this will be our, let's say, performance evaluator. I mean, at the end of the day, I'm asking if my AI algorithm, my autoencoder, where this peak enters and then I got a peak at the end of the entire chain, how much, what is the error in when I calculate the charge from the initial real, let's say the true signal, and when I calculate the charge out of my sample, compressed and decompressed signal. So we are using this indicator as the quality, if you like, of your entire process. And if it doesn't work, we know that we have to change the architecture of the system, because if we see that the error, if I can tolerate a 10% error in the charge, because for any reason, I'm not interested to know the charge better than 10%. I can have an algorithm that is faster, smaller, can be, much more, much easier than obviously if I want a higher accuracy, where the algorithm needs to be, more smart or have more flexibility. what we say is expressivity of the model. So at the end of the day, we want to check the integral, compare what we had at the beginning, what we are going to have at the end. And so the way how we build the autoencoder, remember the autoencoder is a spatial, let's say, algorithm that has a certain number of nodes, is a neural network with a certain number of nodes as an input, with the same number of nodes as the output, and then in between you have layers that are, in this case, fully connected. So again, all nodes talks to the close-by list of nodes, and each of them you change the size of the nodes that you have in between. In this case, we are starting from 48. So the first node is 48 inputs because we have 48 samples. Then, for some reason, you go to 96. That is not good because we are expecting to compact the information, not enlarge it. But this is, again, that's because it works better than going straight from 48 to reduce a number that is 12. So you have 48 nodes, then it goes on 96, then go back to 48, and then finally go to 12. This is just to add, flexibility to your model, to have more ways that you can change and get the performance that you want. Okay. At the end of the day, you get this dimensionality. The bottleneck, as they call for autoencoder, is going to go from 48 to 12. So we are expecting to have a reduction factor of 4. Okay, because you start from 48 numbers that characterize, that define your signal, and then you end up with 12 numbers that you have just to save event by event, knowing how the encoder and the decoder part that remain the same for all samples. So it's a factor of 4 of gain. For that specific signal, because we already mentioned that if you had, for instance, an exponential is easily parameterize at the end. You can compact your hidden latent space in only 2 variables. As you, again, human brain can imagine, you have a height of the exponential, and you have the decay time. In this case, the signal is a little bit more complicated, and then to parameterize efficiently with the network, you need to have at least 12, let's say, numbers, 12 parameters, if you like. That they will be saved at the end of the training, of the test sample. So, okay, another important part that this specific network, we want to use it immediately after the front end. So the amplifier or whatever detector is producing your signal, you want to immediately compress this data, because then the data will move on the network. So you want to keep the traffic low from the very beginning. So in principle, you want to have these algorithms working as close as possible to the origin of the signal. So usually you can use very fast hardware, because you have to do that, quite rapidly. Consider that this obviously depends on the rate of your signal, depends on the number of points you have in your waveform. But let's say that we want to implement on FPGA. This is at least what EPIC is planning to do, to have this kind of filtering and data reduction from the very beginning. So you want to implement on FPGA. FPGA is not a generic, or let's say is a specific hardware that work with numbers that are integer. While you can imagine, we discussed it yesterday, weights are intrinsically, if you like, they are real numbers, because usually they go from 0 to 1. Okay, it's just a matter where you put your comma. It's in the number, so you can imagine that transforming a real to an integer at the end of the day is just reducing the number of bits that you have to code that number. So you do a kind of an approximation. The approximation means that you are, compacting your initial number in a smaller number. So you are losing part of this information. So we want to do that. So we need to have the network that works with integer rather than, so we start with real numbers, but at the end we want to get to integer. And we also want to, as much as possible, have a small, compact network. So the number of weights that we want to use should be limited, because again, FPGA is not like the computer that you are using has a dedicated RAM that usually is not as big as the one that you have on a computer. On top of that, you can imagine that you have so many channels that has to be connected to the input of an FPGA that you want to save the RAM. And then again, there is a need of reducing the size of your network. Okay. As an example, we are going to use the data set of 25,000 waveform that were the ones that I showed you before. Actually, they are really, the waveform shown here, they are really taken with the flash ADC. This is a 250 megahertz flash ADC. That means that each sample here corresponds to 4 nanoseconds. Okay, so this, you see, this is a quite rapid signal produced by the detector. I think this was a calorimeter, like a very constant crystal that produced this signal. This is just, just to give you an example of a reasonable signal that you have to deal with. Then we are going to have, as remember, we discussed that you have to have, you're over the 25,000 sample you have. What we want to do is to split them in different data set. One will be for the training. Another will be for the test. That should be, the completely unknown from the autoencoder to be sure that everything works when I'm going to plug in my network to new signals that are, unknown. So I'm expecting that I want to test everything on something that was not used for the training. And on top of that, we are going to use also a validation set. Validation means that while the system is training, I can take, a fraction, usually 10% of the training part, that is a 10% or a fraction of the entire test bench you have, to check the quality of your convergence. This is, a lot of tricks, a lot of details that are mainly useful to make the convergence, in a reasonable amount of time. You don't want to spend, a year waiting that your network tells you that your charge is factor 2 wrong with respect to the first one. So there are, all these kind of tricks and optimization. We are going to using the mean square errors as loss function. We are going to use Adam as optimizer with a learning rate of 10 to the minus 3, but we'll see that again, there are some tricks to optimize the gradient descent, changing the optimizer along the way, the learning rate along the way, because you start from a course, let's say, step, and then when you are more or less sure that you are close by to the minimum, you want to explore it and scan it.
May I ask you something today? So you're using TensorFlow. It took me forever to understand how to code loss function, which is say high square, instead of just the distance from points. To introduce also take the distance to the prediction squared, divide by the error squared. What you're using here, is it just mean square?
This is the mean square. This is the standard mean square.
Standard one. So not
the standard one.
Not the custom.
No, this is not custom. This is just the standard one. If you want to implement something more fancy, that obviously is, can be requested, you have to be a little bit careful, because there are some dependencies. There are things that the libraries are, expecting that you have to change in all places. We are going to use 100 epochs, maybe not enough. We'll see if we have a practical way to understand if going through your training sample 100 times is enough to train your network. We'll see that this is a reasonable number. And we are going to use as an activation function the ReLU. Keep in mind that since we want to implement the network at some point on an FPGA, and this should be, again, only dealing with integer, also the activation function can be tricky. You have to use something that, is easy to code in nothing fancy like a hyperbolic tangent or, a sigmoid, other stuff that are more complicated. This requires libraries, mathematical libraries, even if obviously any computer is approximating to, steps, but just to communicate the FPGA that you are using, a certain function should be as simple as possible. And again, ReLU is exactly what you need. The weights will be set out of the training sample, as you remember. So we go through this training sample, it creates its extract or define the weights starting from random numbers. So the step 0 is completely screw, and then while you go through your data set, slowly or rapidly, your weights gets, in some way converging to a certain value. And the way how it converges, remember, is you minimize the loss function. And at the end, what you want to do, obviously, is to keep these weights, because if I know the architecture is layers that are 48, 96, 48, 12, and then repeat it again, I can, take my weights, download them on an FPGA. So I do, usually this is what happens normally. You do the training on CPU, on different computers, because for the training, you don't really need to be very fast, but you do the inference. So when I am happy with my network, I take my weights, it's just, a small file, I download on the FPGA where I have the same structure, exactly the same node, and this is exactly the same as running on the CPU. This is the way how it works. So I need, at the end of the process of training, I need my weights. And again, the performance, as already mentioned, we are going to compare, because, we want to be sure that what we are doing makes sense. So we need to be sure that the error associated to the charge, that this is the information we are trying to preserve at the end of the chain, is correct. So we can compare true and model. So what the FPGA, or let's say my autoencoder, is producing compared to the original one, and check that they match. And then again, at the end, weights will be transferred to FPGA. So we are going to use, just again, to give you a feeling how it works, we are going to use 3 models. We start with the standard model. Not standard model of particles, it's the standard model of this autoencoder. So it's running on CPU with the basic, let's say, standard routines. And then you move to another one, reducing the 0. So get rid of small weights. To do that, you cannot just simply, I see a weight that is 0.1 and then I put to 0 and that's it. No, unfortunately, it's a little bit more complicated. You have to tell the network that this 0.1, I want to have it 0, or at least you tell the network how many 0 you want. The size, sparsity, or the number of 0 with respect. So 0 weight with respect to the total number of weight. And then obviously, since you are changing some of them artificially, the network needs to readjust the weights that remains to reasonable value in order to get the same performance. Okay, so this requires a new training. And after this is called the pruned model, the second one. And after that, we are going to have the third model. That is, after that, I reduce as much as I can, keep out, small weights, or reducing or increasing, let's say, the number of 0 in my network. So I know that, only few of them will be significant. Next step will be to transform these weights in integer. And again, unfortunately, I cannot just say cut the weights. I need to retrain everything now, considering that my weights need to be compact only, let's say 8-bit in place of 32, something like that. Okay. So, and again, this requires a retraining of the entire model. These are the performance that you can see on the Jupyter Notebook. Baseline model, this is the loss function as a function of epoch. So you start from random weights, so you can imagine that your error are big. And at some point, it goes down, and at some point, you see here a jump, and we'll see in practice that this jump is due to the fact that you change the learning rate in a clever way. The libraries already take care for you, telling it that you want to go a course step, and at some point, when you are pretty sure that you are close to the minimum, then you want to explore very precisely all the environment to be sure that you really are picking up the minimum and not, remaining closer to the minimum. And you see that also, this is also showing that probably, in the range of 100 100 epoch. So 100 times I'm gonna go through the entire data set is reasonably good because you see here that any improvement is gonna flatten out, so it's difficult to obtain. Maybe if I train for a month, you may increase this result, but it's much easier to change architecture in case I'm not happy with that, if I can. Okay. So here's the baseline model, and here is the comparison of the original waveform, that is the black one, compared to the model, that is the red one. And you see that it's doing a pretty good job. This is just for 3 samples. And also, but this is not enough, because I may, by eyes it's difficult to judge. So what I want to do is really calculate the charge, because at the end I'm interested to the integral here of the peak. I can check the original, the reconstructor, after going through the autoencoder, and define the error. And you see that it's less than 1%. So it's with this, we'll see that it's running in a minute usually, and we are running on resources, who knows, there are, completely shared among the entire world. So if you have your own GPU on your desk, it's much faster than that. It can be very, very fast. So it's you see, it's a compression that gives you a factor of 4, because we're reducing the number to 4, with a loss of in the range of 1%, on an error on the charge that we want to sample at the end at the level of 1%. The prudent model, I'm expecting that is not going to perform as good as the first one, because it's kind of reduced in ways I can use. So I lose some expressivity of my model. I have less parameters, let's say, to tune to get the correct value, but still not bad, because you are in the range of 1% and 2%. And then when you go to the quantized model, again, you have similar performance. At the end, you remain within, let's say, around 1-2%. So it seems that we found a good, actually, thanks to the guy that did it. This was not so trivial. Simplified. I spent time to obtain these results. But spending a little bit of time, you can really find what you need. In this case, I want to keep my error, let's say, within 1-3%, and that's it. This is fine with me, because I don't have my charge when I know it at few percent is fine. And this is also, this is the sparsity. So this is after that you prune the model, how many, the way how the system decide which weight needs to go to 0 and which one remain different from 0 is like magic. At least I have no idea how the system optimize the network. But at the end, and also how distribute this 0 from the beginning, from the first layer or along the way, because we have different layers. Remember, 48 to 96 to 48 to 12. So there are many weights in the different layers. And so this is a calculation of how many 0 you have per each layer. What's the advantage of doing this pruning procedure? And here is the comparison of the original model and the pruned model. You see that, for instance, all these weights were put to 0 by the system, by the optimization process. They were different from 0 in the original, now are 0. But the other ones, okay, this one was very small, 10 to the minus 5, and goes to 0. Okay, makes sense. This one was 2 to the minus 1, and now is 0.22. But you see that it's not exactly the same number. This is because putting to 0 this one here and this one here automatically require the other weights rearranged to get the correct loss function. And you can see also from the way how the pruned model, let's say the loss function on your data set. You start from a state of data, a state of weights. I didn't show here because the first 5 epoch you get to the sky. So at the beginning it's completely wrong, and then rapidly you go down. At some point you flat out. This is a typical way how the machine learning algorithm learn. And here you see that it's a little bit more tricky. It's less easy to interpret, but you have jumping up and down, because probably it tried to put some 0, found the wrong configuration, then go back with one step. Actually, we'll see while we are running the code that the way how the pruning is made is together with the weight that you want to reduce, is also increasing the number of parameters just for the sake of doing this, let's say, this operation of pruning the model. It's adding up a lot of information that then can remove it at the very end. Okay, it's almost the same number of parameters that we have in the network is also the number of parameters that it uses to do this optimization. But at the end of the day, you obtain, and again, same thing, similar thing for the quantized model, where the behavior is a little bit more understandable. Okay, so data preparation is another important part. You have to feed your data in this is a standard. It's a standard format. It's just a table. This is Python actually that take care of doing all this the data file manipulation. So it's very simple. And the way how they were written in the file had first of all a time information plus the 48 samples. So I need to tell the system ignore the first sample and go from the second to the last that you get the 48 that you need to inject to the network. This is okay, stupid detail, but just to tell you that there is also the possibility, or very easy to have a table with your data, with in this case with your components of each data that can be easily changed, increased, or getting other information that you don't use during the process. Results, final results is comparison of the three. I'm spoiling, from the very beginning, but I think it's better to understand, all steps, and then we go one by one. But just to give you where we are heading, okay, where we should head, because I hope it's working. So results, you see that again, comparison by the true, that is really what you start from. You compare to the baseline model, to the pruned model, to the quantized model for a couple of samples. So you can do that for 25,000 events we had. These are taken from the test set. They were not used to train the system. They were in some way fresh, new, not the one that we use to supervise and change the weights. So, this is a remarkable result. And also you see here, again, the error reported for each of them. It's probably more significant is when you look at the distribution of errors, because we have 25,000 samples. So, you want to be sure that it's not, that you by chance, you get the only one that where the pruned model is very good. It's bigger and better than the original. So you want to do a statistical distribution. And what you can observe here, obviously the original, let's say the model with all weights, where you're starting from is better than the other. This is reasonable. The pruned model, for some reason, is worse than the quantized model. And this is not clear why for that specific architecture, that specific, maybe possible that being the quantized model, the third retraining of the weights, it may be possible that this give a boost, let's say, to the weights and rearrange in a better way. This is again like black magic. We try, to increase the first epoch, not to I think 100, but 150 or something like that, or changing also the size of the sample, but didn't change much. It seems, kind of specific feature of that. And you see that the quantized model is performing almost better as good as the original. So we are happy because it means that we can plug in our FPGA, obtaining results that are very similar to what you get on your CPU, on your GPU that you have. And also another, let's say, benchmark to understand if we are doing good or bad. Here is the mean error and the standard deviation. Again, you see that 1.4, 2.7, and 2.2. So actually, the quantized model, pruned plus quantized, is better than just the pruned model. I just want to draw your attention here. The time that you need to run the model now is 200. Okay, it is whatever unit it is. Doesn't change much when you change from the baseline to the prune and quantized model. what is interesting is the size of the model. It is 82 kilobyte that in quantized, it didn't change much in the prunet. And you ask why? I mean, we did all this, business to reduce weight to 0, and then, the size of the network is the same. I mean, the number, because 0, if you have to write a 0, number 0 is exactly the same size as writing number 35. Okay, this is the problem. So I'm not expecting to have a gain in size just pruning the model. It is simply reduce the number of weights. So in principle can give me an indication if I can reduce the entire architecture, for instance. While there is a significant gain when you move from the pruned model to quantized, again, because in this case, numbers are not anymore converted in 32 bits, but they are 8 bits or 16 bits, depending on how you define your integer. Okay, so this, and you see that there is a factor of about 3-4 in size. So this is the size of the weights that at the end of the day is the information connected to this. I don't have the original file, but you can easily imagine that since we started from 48 points and we go for 12 points on each, you have a compression factor of 1 to 4. Okay, so clear? And here are just some, this is, we are not gonna check that, but if you change, I mean, the time that it takes to go through different size of different layers obviously increase. Performance gets better, and this is certified by the loss function that gets better and better if I change my number of nodes and I retrain, I mean, restart from scratch and do exactly the same procedure, changing, step by step. And you see that obviously if I use a super dense neural network with a lot of parameters, obviously it takes a lot of time, but I may have the chance to get a better result. Okay, it's not completely sure, because you see that at the end I'm not gain much. I'm gain if I move from here, let's say, to here, but maybe the next step, so increasing the number of layers, doesn't help much for that specific problem. Okay, doesn't mean that with another waveform, with another different encoding, different kind of signal you have, this may be not exactly the same case. Question, comments before that we go to the Jupyter notebook? It's all clear. So I hope that I give you the the context of why we're doing that, and then there are obviously technical details on how to do it, but at least we understand why we are trying to do that and what are the results, if we are happy or not about the results we obtain.
So on slide 4, you have test validation.
Yes.
Or train validation, test.
Yes.
Slide 2 validation.
Because I mentioned that we were a little bit, confused by the fact that when you move to the pruned to the quantized model, you had your loss function gets better. Certify again by looking at the error. And so we were thinking that one of the possible cause of this, because in principle we are repeating the training several times on our system, but we are also checking on the validation sample. So we are using a training data that is a group, certain amount of data. Then we are using a fraction of them, another that is independent on the first, to check during the training if everything is going right. And we also look at that. The system is also looking at this validation loss. Now, since we are cheating, because when we go to the second network and we start again with the weights obtained by the first, but the training on the second, we are reusing the same data set that we used for the first. That is not statistically correct, because you should start from another training set. So we thought that one possibility was that we were faking, we were messing up with the statistics. So if there are some assumptions here that the training set, the validation set, and the test set, they should be exact replicas. Only statistical difference. Obviously, as we discussed yesterday, if I'm injecting, I play with my autoencoder with the triangle, and then I try to recognize a square, it doesn't work. This makes sense. I need to have triangle all the time. The only difference should be a statistical difference between samples. Okay, so we try to, try to change the validation sample and use a different set rather than reusing the same. But it didn't work. I mean, more or less remain the same. So this is not the cause. We thought that maybe, the reason was that you were running multiple times on the same data set, that this is not allowed. I mean, in principle, you should use all the time new set. This is the reason why we use different validation.
And then why are you using such non-standard splits? Because normally you do like 80, 10, 10.
Because it works.
70, just because it works.
Because it works, yes, just for that.
And when you do the quantized prune model, is your loss function also quantized?
Exactly, yes. Also, the activation function, yes, is quantized.
And that doesn't account for better performance because it's having.
Maybe this can be a good point. We didn't think about. We can try to change. The activation function and check if it gets different in terms of results. This can be the reason. Yeah, because if you look at the loss function, for instance, this is a validation. Validation is a subset of the training sample that you are using while you are training to check, real time, if your new set of weights is getting better or worse on the training set, okay? So you're expecting that the validation, since you are not supervising on, this is an independent set that should be always worse than the one that you use to train the network. And this is the reason why in baseline and prune model is exactly as it is. I mean, the validation loss, the loss function calculated on validation subset is usually worse than the one that you obviously have on the training part. But you see that they invert in the quantized model. It seems that the loss that you calculate is on the training that should be better is worst. The validation, the loss calculated on the validation sample gets smaller. So it means that it's performing better on the validation that doesn't know anything about, rather than on training that knows everything about it, learn out from the. That is something weird. Okay, so maybe it's also the use of the different activation function. This is a good point. Other question, other comments? But obviously, I mean, we can during the run, you can play with that, changing parameters, changing the size of the. It's very easy when you change a line of code, and that's it. And you use other than this case is 20%, 25%. You can use 10% and check what happens if I increase my training sample rather than compared to the test set. So this is really, as soon as the network is provided, this is really easy to do.
Marco, sorry, we have a question.
Oh, sorry.
I might have missed it in the beginning, but how do you set?
Sorry.
I might have missed it in the beginning, but how do you set the initial weights to the network? Or do you?
It's a random. The first set of is all zero.
I see.
Obviously, you get totally wrong values. And then you say, no, 0 is not good. Let's move this weight to 1 and check what happens. And then you have this rapid learning from the data set, comparing what you get in with what you get out. Okay, you make the difference, you calculate the error, and if it is big, you are going to go down to the gradient. You are doing a derivative in a computing way. I mean,
That's what the optimizer does for you, right? It calculates the change in the learning rate as you train the model, and then it.
Exactly. This is exactly the step you are using,
Yeah.
because every time you change your weights by a certain amount. Okay. And I showed yesterday that if you have a parabola, that is obviously you have a multi-dimensional, it's much more complicated. But assuming you have a parabola, if I make my step too big, I'm jumping out of the minimum. I never get the minimum. So the idea is that at the very beginning you are far away from the minimum, so you can have course steps very large. Actually, it's helping you, because if you go in the wrong, let's say, valley of your multidimensional loss function, if you do large steps, there is a good chance that you run on another ones, and then you remain and find the correct absolute minimum. That is what you are looking for.
Another question that I have is that if you use dense layers in your network, in which every neuron is connected to every other neuron in the previous layer, is there a chance of overfitting in that procedure?
The chance to overfit is always present. It's not strictly connected to the architecture. It depends how many nodes you have in the network. It depends on the expressivity of the network. More weights that you have, you feed it, the higher is the chance that you are overfitting, that you have a perfect replica of the training set, but as soon as you try to apply to something, we saw yesterday with this polynomial of high order, that if I have sparse points distributed, I can find, order 50 polynomials that go exactly through all points. But then I had another point that obviously the chance that is really going through it is wrong. This is the tricky part. Again, the variance versus the bias. You want to minimize the error of your loss function. I mean, you want to have a replica, or your model needs to be as close as possible as the true, minimizing the error, but at the same time, you may find a solution that is not exactly, the true, that is the bias. Okay?
Thank you.
Okay. So if you connect it to the Jupyter notebook, again, all credits to Fabio, the guy that wrote it, and wrote also, I hope, detailed description of steps by step, so it should be understandable. So first of all, you just import the necessary libraries. This is kind of standard stuff that you need along in notebook. Again, you are not used to use a Jupyter notebook. You see that there is some text here where you can place figures, etc., and then you have a part where you can really code. And then for each block of code, you can execute just run it. But before to run it, we may, with that specific with Colab, you can also choose. This is already TPU. This should be the faster. Depend on how many people are using it at that moment. The resources that they provide. Anyway, so this is good. We like it. And then for each part, you run. And if everything goes right, it tells you how much it's taking in terms of time. Okay, and I know that it's going to go from this point. This is just importing libraries, telling the system that they know when you refer to a certain function or class, it knows what you are talking about. Okay. Then optimization again, other libraries that you need to have to work with Kera. And then you have data. As I already mentioned, we have these 48 samples, and here is the file where the file sits. It's a CSV, so it's just Excel-like format. It's very. My background is not in Python; it's in C and C++. I'm really surprised that there's really a waste of resources. We are using root to have very compact files where you save your information. Here in Python, you write numbers in that clear mode. That is crazy, but probably resources are so infinitive that you have. And this is another problem when you try to optimize your code, to run the code on dedicated hardware. Using where you have to be careful in using resources. You don't have infinite resources as you have on the CPU nowadays. So you have to be, a little bit more careful on that. But anyway, so this is the standard way. You have a CSV file that is exactly the file that if you click on with the right button on that. This doesn't work. I don't know. It depends on the browser.
Just probably highlight it.
Oh. You should open the file. I was able.
Yes, just
Here, no?
just
Okay.
highlight the address. Put it in the.
No, but it was automatic. My browser was opening automatically.
It should.
Copy. Anyway, so if you find a way, you can see the file that is, this 25,000 now multiplied by 48. Okay, so you just use, pandas and other standard library to do plotting and, show what we were discussing so far. So I ran this part of the code. This is just showing the first three. I mean, if you want to show four, you write here four. Okay, and this is just to give me a sense of which kind of signal I'm trying to encode. Then there is a definition of a function that allows me to calculate what I mentioned before, the baseline, and defined as peaks. I know where the peak is, and then I go 3 sample before and 8 sample later, and I define my peak in that area. Okay, so it's kind of dynamics as a clever way. I don't know where the peak is within the window, but I know that the length of the peak is always 11 samples. And this is enough to define correctly, as we'll see, as you see in the example. Okay, and then you calculate the integral just as a sum of your values of y of the digitized samples. Okay, there's nothing more than that. So I ran this part here that is just defining the function. Fabio tried also to do, more fancy integration, because in principle you can use other way. You can use trapezoid rather than this is, is a brutal approximation. You have a quantized function that is just a step function made some way like that. You can either sum the value plus this value and assume that this actually the real function will be obviously something smooth, or you can do something more better, like approximating from here to here using a trapezoid. This is a little bit more precise in the calculation of but this is not the sake of the exercise. If you want to calculate the integral in a better way, there are other libraries that do that for you, trapezoidal, Simpson, etc. Okay. So we run this just definition of the and also at the end of this function you get the fancy, the nice plot with the peak highlighted in blue and the baseline what what remain outside the peak in red. So if I run it, it's going to calculate and also calculate the integral, because again this is at the end of the day what we need to be sure that the machine learning algorithm is reproducing correctly. And then we go here to the training, how you split your original training sample. You see here, and you have the different. You give the percentage of how much you want in each of the different data set. So in this case, 50% for training is 15%, 12%, 25%. I mean, you can play with that and check if results are good if I change it. Okay, so now it knows that we have 3 different or 4 different data sets. I mean, we split the original data set in a chunks, and then we can finally define the network. This is the core, the significant part where you define the number of input layers, the number of latent dimension, in this case is 12, and in between you define it, the other layers that are less significant, because you want to be sure that you have 48 and 12. What is in between is less relevant. And you see here the way how it is defined, that it takes, input size, and then you use a second layer. This is let's say the second layer uses an input the first layer, and the third layer is used as an input the layer before. This is in some way defining the structure of your network. And when you are done, when you get the 12, at 12, the output, then you do the opposite. You start from 12, you go to 48, and then you go to 96, and then you end up with 48. And you see here, 24, 48, 96. And then there is the final value. Okay? Input size, because obviously this is an autoencoder, so I want, starting from 48, I have to end up with 48 if I want to see a signal that is similar to the one that I used. Okay, is all clear? So this is the way. I'm not the Keras doesn't. I don't tell it that I'm using an autoencoder. I'm building a network that has the what I call autoencoder. Okay. And then again, I call it baseline model, but it's just a name. And then I run it. It is just defining internally how the structure of the network is with this part, and is printing the summary of the network. Okay, so you see here we have 96. So how many parameters you have? Remember what we said. You have weights per each node. So you have one weight, and it goes on the different connection. So I have a 96 by 48 plus the bias. There is another set of 48 numbers that I am adding up to the weights. So this is the reason it makes 40,700. Okay, clear? Then same here. We go from 96 to 48, 48 to 12, 12 to 12, etc., etc. 12 to 12 should be 144. It is easy. We can do it. Wow. Easily, and it is 156 because then you sum up 144 plus 12 bias. Okay, and the same on the reverse on the decoder part. And this tells you that we have in total 20,000 parameter, so it's not much. I mean, it's a quite small network with 80 kilobytes. So again, something absolutely small. All parameters that now implemented in the network, they're all trainable. Like all they are going to be changed at epoch by epoch. And so tell me that it's exactly the same. We'll see that when we move to pruned or to quantized, is adding up parts in order to do his internal business to optimize. So at some point you have a network that explodes and then gets back to the correct value, correct size at the end of the procedure. Again, I didn't mention, but when you define each layer, you define the function, the activation function you want, and then again you can play with the ReLU, with the ELU, with the whatever function, and see if results are good or bad. We tried, for instance, with ELU, and it didn't change much. Okay, this is just to show the difference between the ReLU and ELU. We started with ReLU exactly for the reason we were mentioning before, that we want something that is easy to quantize. Obviously, if you have something smooth that require a fine approximation, this is not good for at some point switching from real to integer. While if you have like 2 lines, it's much easier to. I mean, you can imagine that it's much easier to get when you put on integer value. And then we declare that we are going to use Adam optimizer. We are going to use mean square error as a loss function. So we are training on, we want to keep this error as small. I mean, at the end of the training process, we want to keep it small, possibly to 0. And the learning rate, this is a fixed number, is 10 to the minus 3. Again, why 10 to the minus 3 and not 10 to the minus 2? Because it works. I mean, if you go to literature, they say that this is standard way, standard number, but it doesn't mean that it's the best. Okay, so let me just again, this is we are calling a function like a Keras optimizer Adam with some parameter like learning rate that we define here. So it's very straightforward, reasonably straightforward. And then we have this is a tricky. This is called scheduler or callback. This is a series of functions that you can call that during the training will help you in the convergence. Again, this is just the tricky stuff. It's not nothing fundamental. But as I mentioned before, for instance, that I don't want to keep a learning rate constant. I want to, at some point, move to a smaller one, and then this can be done automatically by the system if you use these functions, so-called callback. They have a specific function, for instance, learning rate scheduler that tells me how many epoch you want to use with the standard one, and then I switch to another that is different. Okay, it's a kind of, they call it decay, and you can give the formula of how you want your learning rate changing as a function of epoch. Remember, epoch is every time that you go through the entire data set. So the weight gets rearranged, you end one cycle, and then I go to the second one, get, again, all my calculation, and then a new set of weights, and so on and so forth. And you can, in this way, for instance, you can define your function for, I mean, again, this is absolutely, custom. You can do whatever, what you prefer. In this case, since we are training over 100 epoch, that, is reasonable, we thought that the loss function is good. When you, at 50, in the middle, you started to be more, precise. If I went for 1,000 epoch, so going through 100,000 times over my data set, probably I wanted to use, obviously, a different, gonna go to define steps at the end, not at the very beginning, okay? Okay, so I call this callback. Then there is also some other trick, this early stopping. This is control the validation loss improvement. So check if everything during the training is going in the direction I'm expecting, that you get, better results than the previous, or it stops. If at some point I found that there is no difference between the new step and the previous, say maybe I'm already found the minimum. It's useless that I go away for and keep going forever. Yes, exactly. It's the patient variable that you can define when if I in 10 epochs I don't see a significant improvement, I say, okay, let's stop the training. Doesn't make any sense to go further. And then there is this, and the other important part is that at some point you want to keep this weight in case you need to get the weight out and implement on a different network with the same structure. So you need to have a file where you write all this weight. And this is one of these functions that put in this plot best.h5 in a format that Kara is using. It allows you to keep the set of weights. Okay, and then you can take and feed them to another network, or we'll see that when we are going to use the prune model, we are reading out this set of data because we don't want to start from scratch. We want to start from the best configuration found and then move from there, rearranging the weights, not starting from zero. Okay. So I already compiled this part, interpret this part, and then finally, this is the part where we are really going through the training. So number of epochs, we say 100. I am declaring how it's called the train data sample, train data set, that is called train sample. And we are using the same train sample at the beginning, at the end, because I want to compare. I want to be sure that going through my autoencoder, I have my waveform, and I compare with the same waveform at the end. I want them to be identical, or as much as they can. The 48 numbers that define the waveform at the beginning and at the end, they should be close to equal. Oh, this is an average. We are summing up the error of each of them. So it's not exactly that each sample will be exactly the same as the other sample. Okay, it's on average. And then again, this is declaring number of epochs, the batch size. Also, these are tricks that you're using. Just not that you give before the changing the weight rearrangement, you can decide to use only a fraction of your data. And again, the training depends on all these parameters, and they were optimized just by changing. And again, the suggestion is to try and to see what happens if you change these numbers. Okay, and then I run it, and this is now training. I mean, it's loading all stuff and is doing this weight rearrangement. Takes a little bit because it goes on 100 times. Okay, the first part is just to define, and it's pretty rapid, you see here. And at the end of each epoch is printing the loss function, and the loss function is calculated on the training set, and the val loss that is calculated on that other sample, just to check that the two are not diverging, because to avoid in particular this overfitting, I want to be sure that if I use a completely different data set, my results are reliable, are still good. Okay, and then
save the model after each epoch.
Sorry?
You save the model after each epoch. Is it improved if you save after you perform?
No, I think that is it started from the previous step, but I'm saving the weight at the end when I'm happy at the end of the training.
So it's every time, it's every model to flow best of each. No, but it's okay. I was just thinking about the improvements. It takes some time to save. Why don't you save at the end?
Yeah, but I mean, we are not limited on neuron performance.
That's right.
Okay, this is just to have all this debugging, you can also put the verbosity to 0 to have a faster. But usually, the training part is not the long one. It's more when you want to use it. I mean, you don't care if you spend a week doing the training, not a week, probably not a year, but it's more important when then you have to use it. This is not optimized at all to run fast.
It'll only save, because he has save best only. So it'll only save when it improves, and it's only saving one.
Okay, and now that we have, I think that now, yes, we can check how the loss function gets better over epochs, because I want to save the information at least epoch by epoch on the loss function to plot it and show. And again, you see here that there is around 50. The learning rate here is not very visible, but it's gonna go in a different slope. And this is the final value. So are we happy about this number? Are we not? I mean, this depends on us and results that we obtain. It's very difficult to say if it is good or bad. Just judging from here, again, what I can say is with this architecture, with these numbers, it's difficult from 60 to 100, there is not a big improvement. So probably it doesn't make any sense to go to 1,000. With the same architecture, maybe I want to change parameters, I want to change the different numbers that enters in this procedure. And then finally, yes, I'm saving at the end the one that that I consider the best model, because it's at the end of my training session. Okay. Okay, and then finally, yes, this is to evaluate the quality of the result, and just defining how you calculate the mean value and the standard deviation. It's just simple functions. And then we evaluate running over the entire test sample, what is the results on from the original one and the model. Okay, just because I want to use as an indicator the charge, this integral of the scene, and I want to be sure that what the autoencoder is doing is not screwing up the information that I want to preserve. that is at the end of the day is I want to calculate. Obviously, you can imagine that in the real life, I'm not gonna use the auto-encoded waveform to calculate the integral. I'm a little bit smarter than that. I'm gonna calculate the integral at the very beginning on the true sample and moving this information up to the end. Okay, and I keep the waveform just as an extra information. So I calculate with a minimal error the charge. So in that respect is I'm cheating a little bit because I want to have a good integral just as an indication that my waveform is correctly reproduced, but that is not what I use in real life. I want to use as much as I can the original information, so the charge calculated from the original waveform. That is just a number, so it's not heavy to move along my procedure. And again, here you see the comparison of the amplitudes calculated with the model and the original, and also the error. And you see that it's doing a pretty good job, even if you see the peak is not always in the same position, but it was able to find, to understand. Sometimes it's at the beginning, sometimes it is at the end. It's working pretty well. Okay, so we are happy. We have a model that works that can encode, divide by a factor of 4 our original data size. It's not bad. And then we move to another step that is trying to prune the model, so trying to get rid of small weights. And again, we can define, there are some trick here, you define what is the sparsity it has to start from. We say that, we want at the beginning, you get rid of 50% of weights. You want to put 0 in 50% of them. But at the end, I want 80% of them to be 0. And this helps again all the process, because if you are too drastic and say no, I want to just say start from 80%, maybe that you screw up your network and doesn't. We found more or less a stable situation. Now you are changing too drastically your weights, and then you have. I mean, the training doesn't work. Well, in this way, you can a little bit adjust it. So initial and final sparsity, what they call it, sparsity. And it is still running, I think, on the again, where I think that here you can also decide if you are expert, you can tell in which layer you want to prune. So you can in some way steer the process. If not, you automatically, and they choose where it thinks that the algorithm choose where it thinks that should work better. Okay, this is the case. I mean, we didn't fix which layer we want to prune. Let's say just prune whatever. Okay, then what you want to do is to not screw up the original model, because at the end we want to compare, so we need to copy, the structure of the network in a new network that we call it prune, with weights that will have as a starting point the previous weights, and then will be trained for a while for a certain number of epochs. So I'm cloning, let's say, the model as it is, and this is, you see, the new pruned model with parameters. In this case, you see a lot of non-trainable parameters, that almost the same number of parameters, 20,000, that gets added to the weights and bias, just for doing this. This is probably keeping a copy of the original before changing. It needs to have all the time the starting point clear, because if you go in the wrong direction, you want to go back by one step. So mainly duplicating the number of parameters. But some of them will just be used during the training phase, and then get rid. At the end of the day, we are going to get the same number of parameters we started from on the other network. Okay, and then again, you define these callbacks, this quantity that you need to optimize, and also we define the file that you want to save the weights in, that we call pruned. Same thing. In principle, you can change also the way how you are optimizing, because in some sense you are starting from scratch. It's not necessary to go through the same exact steps that you had in the previous one. And then finally, I think you have again where we are running on the trained sample. This is the tricky part that probably is not fully correct statistically because we are reusing the same training set we used before. That should not be allowed, and we are using the same sample to validate the training. We are using the same block of data that we used before for the pruning, while for the quantization, we are using a different data set. And again, you run it. We are training only on 30 epochs rather than 100 because we are starting already from a very good situation where weights are almost stable. Obviously, there will be some fluctuation as I showed you before, and now we'll see real time. When the loss function gets initially. On the loss function calculated on training is reasonably good, but as soon as you switch it to the other data set, you get a factor of 2 words, and then goes up and down. But fortunately, after 25 epochs gets flat, that is good because it means that it found a reasonable minimum. Okay, and here, save the weight, and strip, yes, because at this point you want to save the weights without the 0. I mean, you want to replace this part that was not used with zeros. And again, you calculate your distribution over the test sample if the integral gets reasonably good or not. And you want to compare, as we did already, your wave function, waveform after and before. I mean, the true compared to the true results, and you see pretty good with error that is bigger than before, but reasonable. And then here is the way how these are all function or all of Kera that provide this information. So you get the weights for the original that is stable, and then you compare with the other one here. Actually, I don't know why it's changing over time because in the slide I ran exactly the same notebook and the weights were different. So this is again showing that even if we have a number at the very beginning that we use in principle to have reproducible results, there is a random seed, let's say, that you can set at the very, in the old system, you see. A random seed is fixed. So in principle, every time that you run from scratch, it should give you the same results, but it doesn't. So maybe also running on different hardware because this on TPU, the other was on CPU. And then, okay, say pruned model, we got the weights. You see that many of them were 0. And so only some of them are a little bit rearranged. This was 0.19, now it's minus 0.2. So it's a little bit different, compensate the one that we put 0. Okay, and then this is just again to give you a feeling about the sparsity. So how many 0 and where it puts 0 in the different layer. And you see that 80% on the first layer, and then again 80% on all of them. Because we asked it to have 80% in all layers. Then we have finally the quantized model, and we go exactly through the same steps. So you start from the pruned model, and you define your optimizer in its usual steps. Again, in principle, you can use whatever you like. I mean, it's not necessary to reuse exactly the same thing. If you go to the new one, building the network with again a usual number of nodes, but in this case it's called quantized because it knows that it needs to keep number, integer number rather than real. And then in this case we just train for 10 epochs because we hope and we are changing a little bit the structure on starting from the previous point. And we are also using, as I mentioned before, you can try to use this sample piece, the second sample data set, as a validation set. It didn't change much if you use the other one. We thought that probably is a problem of the way how the activation function is treated by the integer part, I mean, by the quantized network and compared to the standard one that makes it. Anyway, again, you said the checkpoints, it's running and providing results, and okay, run over 30 epochs, and then you can finally check how that is different from what I had. And this is maybe a little bit, but still, yeah, validation loss now gets, larger and smaller. It's not all the time smaller than the other. So I don't know what changed from one to another. I have no idea. But now it makes more sense. You're expecting validation loss worse than the loss calculated with trains. And finally, again, you evaluate the quality of the model, calculating the average of charge, making the difference between the true and the final, and calculating the error. Okay. The mean is 0, so I'm going to get the correct Q, correct integral, and there is an error a little bit larger, 2.2%. Okay, and I say that we are done, because now it's just a matter of comparing the different, no, sorry, this is still the database means, the true, and you compare to the quantized model, and you see that they are pretty similar. So we are happy. And then he wrote this part that is a detailed, comparison of the different model, plotting the different quantity. I mean, the true model, the original model, the one we started from, then a true net model and quantized model, and you see that all of them are more or less matching. So we are happy. We're really happy about that. And also, this shows up when I use my own evaluator, if the charge was calculated correct, if the integral is correct, it's telling me that all of them are around 0. So the difference between the true one and the one after the autoencoder is correct. And just there is some error in this operation of so it's a lossy. Clearly, this is a lossy compression. It's not lossless. I mean, we are losing something. We are adding some noise, at least, to the system. But again, depends on us if we are happy with a few percent more or less. And I say that this is really the last cell, because yeah, this is probably some numerical result. Remember what does it here? Yes, it is calculating the size. At the end, you can go through the file or the number of weights and tell you how big is the file, how many parameters you are in each of this model. As we already noticed, there is no gain in size between the baseline and prune, because we have 0, and 0 cost a number anyway to be recorded, while there is a significant gain when each number is not recorded as 32-bit, but as 8-bit. Okay, and you see the size decrease by a factor almost of 3 or more. And that's it. I think that now is, you can copy, and obviously this is the skeleton that you see it works. At least now, I mean, so you can change details. You can really run, changing all the parameters we discussed, and check if it works. You can change the number of nodes. You can change, learning rate. You can use not Adam, but you can use a different optimizer. You can change the loss function, for instance. So it's really, try and see what happens changing the scheme. Okay. So it was long. It was too long. Sorry.
We have no discussion in the evening. So questions, comments to Mark? Is there anybody here who actually programs Python? Okay. So any comments about this notebook? there are zero programmers, those who program with those who program with Camelback, okay? So to those of you who actually program in Python, homework. Please use Keras tuner to optimize the hyperparameters for this particular autoencoder. Okay, there was a question about tuning of hyperparameters. So TensorFlow provides an automatic tool. It's very expensive. I'm not sure whether Google Cloud will like it. So I suggest you do the following. Implement Keras tuner for hyperparameters used for this model. Go around the result that they found and see if you can do better. Probably it will not wield any respect. To anybody else who doesn't know how to program in Python, run this thing, okay? And try at least to achieve one thing. Well, while you run it, it will finish, okay? Okay. So there is this very interesting example of overfitting. Then your validation loss and loss start deviating from each other, okay? Which you can see in all textbooks, but in practice, it's quite difficult to achieve. Okay? And what they say is that once you ramp up the number of epochs, at some point, the model will try to be as perfect such that this will happen. Try in any of the steps, there are a number of epochs, it's modest, 100. Set the number of epochs which you can tolerate, 10,000, and see whether overfitting occurs in this particular configuration. If it occurs for this particular notebook, try to convince us that it does. Okay, so tomorrow, lucky you, we'll start lectures by Stefano Forte, who is notoriously a big expert in machine learning as well, because he's the head of neural network PDF collaboration. Okay, so while you will be doing all this, you'll be able to impress Stefano as well. Okay. Good.
You have to turn off the early stopper to get that to happen. This doesn't the early stopper
Maybe yes.
force it if it starts?
Yes, you have to get rid of it,
Turn
yes.
off the early stopper.
obviously.
So what I suggest, if you don't know how to program, just try to play with it and see what is actually happening.
I found, useful because the scheme is working. Now you can play with different components. Understanding is also very well commented by Fabio. So you can easily, change one step at a time and go through the entire things and see the effect only on one change in a controlled way.
Ideally, you would use your favorite data to implement this for your favorite data. But at the very beginning, I would just stick to what's there. Once you feed in your data, you'll see that perhaps it works. Then that's why machine learning doesn't operate without programmers yet.
Yeah, you can, for instance, you can generate other than, on 48 samples, rather than this peak-like function, something like an exponential, and check with the exact same network if you reduce the latent space size to few parameters and check how, in this case, performs, in the other case, you will see that you can really go up to 2. In the other case, here you can't. And if you try 2, you can just replace from 12 to 2 and see what happens. If 2 are enough to reproduce your results. If I'm happy, probably, with 20% error on my waveform, that's it. I can also use 2 if I want to have a calibration ratio rather than 1 to 4, 1 to divide by another factor of 4. Another factor of 6, sorry. So it's a factor of 24. It is a huge, significant compression.
Excellent. You don't have to do it tonight, okay? You can
So
do it
tonight
tomorrow.
here,
Tonight we'll have dinner at 6 p.m. So we'll see each other in 1 hour, 10 minutes. Georgia. Let's thank Mark once again.
Well, questions, let me pull up the ride board real quick.